Hey guys, back again with another physics lecture. I swear I had recorded this one, but then I went back and looked and I had skipped right over it, so not sure what happened. But anyway, this is structure of matter and atomic theory, and so we'll jump right in. This is out of chapter 2 from the Carlton, Adler, and Ballack book. Principles of Radiographic Imaging and Art and Science. This is in support of the NGH Radiation Physics course. All right, and so we have some terms that we're going to learn: elements, atoms, compounds, molecules, mixtures, things of that nature. But typically we're going to be dealing with elements, atoms, and molecules. Compounds and mixtures are probably bigger than X-ray science as far as scale of effect. X-rays affect atoms and molecules. Talk about the history of classifying matter. Think Mr. Dalton comes to mind, and then Mendeleev comes to mind as far as the fathers of chemistry. The electron plum pudding raisin bread model. J.J. Thomson naming the electron and doing an experiment. Now for the live lecture, there is going to be an embedded video showing J.J. Thomson's experiment, and then also a demonstration that I can do with a Tesla coil that repeats J.J. Thomson's experiment. And I think I'm going to add a magnet to it this time and see what happens. So, because you can deflect a stream of electrons with a magnetic field. So we'll see if I can scratch up. I've got a neodymium magnet somewhere at this school. I just have to find it. So that would be cool. The gold foil experiment, Ernest Rutherford, following on the heels of J.J. Thomson's experiment, where he discovered and named the electron. Rutherford dug a little deeper to try to get a clear picture of the rest of the atom, and he devised the gold foil experiment, which taught him or revealed some key information about the rest of atomic structure. Following on the heels of Rutherford is probably one of the first names you recognize, Niels Bohr in the Bohr model. At least for my high school science curriculum, that was the model of the atom that we were taught. Didn't really get into the Schrodinger model. We did talk about electron clouds a little bit, and I guess that's the Schrodinger model, but we really didn't get into the mathematics of the Schrodinger model. For the principles of X-ray science, the Bohr model is good enough. We don't need to add to the complexity like Schroeder. Now Schrodinger's model is probably more realistic than Bohr's model. Bohr's model is kind of simple, a little bit too simple, and leaves out some important details that Schrodinger's model explains better, but those details are not relevant to X-ray science. So the Bohr model, we like keeping the model of the atom very simple. 3 parts. Each part has a couple of rules to explain why each part is where they are. And it's pretty easy to draw a Bohr model. It's only, you have to memorize 2 rules and know the atomic mass and the atomic number, and anyone can draw a Bohr model. So we will talk about the periodic table of the elements, and I will highlight some elements that are important in X-ray science. And we'll talk about the periodicity, which is the reason we have this table, is that chemical behaviors and behaviors of elements tend to repeat. That is, everything in a vertical column has roughly the same behavior or similar chemical behaviors. So that's why the periodic table is arranged the way it is everything that's stacked vertically, those elements behave similarly. Okay, so structure of matter. So we've got this, we had matter, we have energy, and so what the heck are we talking about with matter? Because a stone and a bucket of water are different. And so we have these terms, substances, a material that has a definitive and constant composition. That would be like distilled water is a substance, okay? It's made out of all of the same molecule. Distilled, meaning it doesn't have any dissolved salts in it or any impurities. It's just H2O, okay? Mixtures would be two or more substances combined. And so most of your stones and rocks are mixtures. Most of your soil is a mixture. And most of the water that you encounter is a mixture because it's got other stuff in it besides just the H2O. Okay? Compounds, two or more elements are chemically united in a definite proportion. Compounds are formed. So water is a compound. Okay? It's two hydrogen, one oxygen. Okay? Water is a substance only when it's been purified. Water is a mixture because things like to dissolve into water. All right, so molecules is typically we're talking about two or more atoms or chains of atoms that are bonded to each other. Okay. A molecule is the simplest part of a compound. So water is a compound. The water molecule is the smallest part of water, the compound, that still acts like water. If you break that apart further into its component oxygen and hydrogen, then it no longer acts like water. It acts like the oxygen and the hydrogen do. Only when those three atoms are combined together do they form a water molecule and does it start behaving like water. Okay? An element is a substance that can't be broken down into any similar substances. So elements would be like iron, copper, purified, obviously, forged and purified, by metallurgical process. Nitrogen in the air, kind of, but it's two. Nitrogen in the air it's an element, but it's also a molecule because there's two of them. And it does say when two or more atoms are chemically united. Well, there's a triple bond between the two nitrogen atoms. They're sharing 3 electrons each. Okay? An atom is the smallest particle of an element that still possesses the chemical properties of the element. Okay? Now for metals, you do get individual atoms. Okay? Oxygen and nitrogen, there's always going to be 2 atoms forming the elemental air molecule that we encounter. Okay? But an atom of copper behaves just like a bar of copper, which is just oodles and oodles of what power of 10 is that, Mr. Tilson? Well, oodles and oodles. It's just a whole lot of copper atoms. One copper atom will behave the same way as billions and billions of copper atoms, to a certain extent. Same melting point, so on and so forth. So, but if it's smaller than you can see, can you really tell if a single copper atom is solid or liquid? You can't see it. You can only see it with an electron microscope. And there's no way to tell what form it's in. So you need quite a few, in order to detect what phase of matter you're dealing with, you need quite a few more than a single atom. But it's handy to think about single atoms because chemical reactions happen molecule by molecule, atom by atom. And X-ray interactions happen molecule by molecule, atom by atom. So, all right. So this is a representative example, and so we should be familiar with this substance, this compound, this molecule. This is water. this is what it looks like if we were to see, and those are Bohr models. So those are electrons in orbital shells, and the hydrogen shares its electrons with the oxygen, filling the oxygen's outer shell. Right? Now, the angle, they got the angle wrong, this illustrator did. That angle between the two hydrogen, if you connect the middle of the hydrogen nucleus to the oxygen nucleus, and then back out to the hydrogen nucleus, that should be 120 degrees. It doesn't even look like it's 90 degrees. Those hydrogen atoms should be separated by about 120 degrees. Okay? And these are covalent bonds, and we're going to figure out what that means, sharing rather than stealing. That's the other option. Those are ionic bonds, where the bigger atom steals the electrons, and then both of them become charged entities, and then they're attracted to each other by a Coulomb force, by an electrostatic force. That's ionic bonding. Covalent bonding is more of a sharing relationship, where the electrons spend almost the equivalent amount of time in orbit around both or all three atoms here. Okay, but water is right on the edge of that. Water is weird, and because of the 120 degree angle, and because oxygen is slightly bigger, 8 times bigger than hydrogen, the electrons do tend to orbit the oxygen more often than they orbit the hydrogens. So we get this special, I guess, property or behavior of water, that it is a polar molecule. Even though it's not ionically bonded, it does have a positive side to it in between the two hydrogens and a negative side to it over on the oxygen end. Okay, and that does explain some of its behavior. That's why things so readily, especially ionic salts, so readily dissolve into it, is because it does have this polar covalent type structure, and it's a function of the oxygen being bigger than the hydrogen, but it's also a function of that one magical 120 degree angle that is poorly illustrated here. I'll say it one more time. So this explains solubility, basically, the positive and negative charge to opposite ends of the water molecule. It explains why so many things dissolve into water. So matter is present in 3 fundamental states, and then weird things start happening in extreme environments, so to speak. And so, but I think we can say plasma. I'm pretty sure everyone has gotten the update. Plasma is the 4th state of matter. The corona of the sun is made out of plasma. The flames of a campfire are made out of plasma. Just about any glowing thing that's giving off heat and light, that's a plasma. Okay, so solid, liquid, and gas, those are default states. And then in special situations, ionized gas in large volume is plasma. Okay, and so you see it in fire, you see it in combustion. The flame literally is little bits of hydrocarbons that might have charge, and then bits of oxygen and water molecules, and lots of loose charges and loose electrons, and recombination. And so it's a chemical reaction, combustion is, and it releases heat and light because it is ionizing the matter as it's breaking the bonds. And so we see that states of matter depend upon largely temperature and internal energy, effectively. We call this internal energy heat, or thermal energy. And so it's a position of the atoms and the molecules. They're jiggling more or they're jiggling less. As they jiggle more and more, they transition from solids to liquid to gases. And those are the easy ones we can see. We can see that with water. Ice is the solid form. Of course, water is the liquid form, and water vapor is the gaseous form, or steam is the gaseous form. Okay, and that largely depends on temperature, which is, I remind you, that is average kinetic energy of the molecules of the material you're measuring. So if something is hot, that means the atoms are jiggling and moving around rather aggressively. They have all the atoms have kinetic energy, and they're bouncing around and colliding into each other. Okay. Versus in a solid, the atoms there might be vibrating, but they're not like just carousing around and moving around with velocity, with what you would call a measurable velocity. They're almost fixed in position, and in most cases they are fixed in position. All right, so where do we get this notion for elements and atoms and indivisible matter? You can go, once you go dig down far enough with anything that is material, you can subdivide it, and then you get the smallest piece. Well, that idea started with the Greeks. The Greeks said that there was a smallest piece. Okay? The Greeks also thought that there were only 4 elements: air, water, earth, and fire. Okay? So they got a few things wrong. They did get logic and reasoning right, but then they just went off the rails on some ideas. But at least they started trying to figure things out and trying to logically deduce things. It's just they kept putting in premises that were just not true. So that's a lot like fire being an element. Fire is not an element, it's evidence of a reaction. Okay. Air is a mixture. Water, okay, they're close. That's a molecule, a compound. Pure water with nothing dissolved in it. And then earth is definitely a mixture. Okay. All right, and so then there was alchemy, but we don't have a lot. Alchemists were metallurgists and chemists, but they so here's the problem with alchemists. Alchemists were seen as witches or demon worshippers by the Catholic Church that was in power after the fall. So after the fall of the Roman Empire, then we see the expansion of Christianity. We see a lot of kingdoms and medieval feudalism and such, and people that were studying science were often scorned by the church, because the church was the one that was in charge of handing out knowledge like it was currency. And so the only correct knowledge was the knowledge the church was. And so if you have control of what is proper knowledge and what is not proper knowledge, then you can control a populace. Okay? And so alchemists were basically, they had to work in secret, unless they were, the pet alchemist of the king, and they could dream up various medicinal recipes and such. And so alchemists are the precursors to chemists, and the precursors probably to medicine and the practitioners. Now, medicine did start in ancient times, but as far as preserving the ideas, the herbalism, the what we would call homegrown medicine or homeopathy today, different tonics and filters and herbals, different. You just brew up a tea. You throw in this type of weed and scratchings from this root, and then you'd boil it for 2 hours, and then you'd sift it through paper to get rid of all the junk, and then you'd get this brown broth, and it would be very bitter, and you'd drink it, and maybe you'd feel better. Well, that was all alchemy, right? Some of it was metallurgy, and a lot of it was trying to turn lead into gold. There were very many smart men after the fall of the Roman Empire that wondered if they could turn lead into gold. And it went all the way up into the Renaissance, and I think Da Vinci was still working on it. He was probably an alchemist too. There were probably a lot of alchemists, but it was frowned upon to practice alchemy because it went against the teachings of the church, and the church were the arbiters of the truth. They were dispensers of the truth. They had basically a monopoly on truth, and so you couldn't go and figure out other truths on your own using scientific methods and ancient recipes from dating all the way back to the ancient Egyptians and the Babylonians or what have you, because that was basically empowering demons and worshiping false gods, because that's where the recipes came from. And so, yeah, so we do have some alchemical record, but not as much as I would like, certainly. I think it's a fascinating part of the history of science, and I think it's largely overlooked. But then Newton came out, and Galileo before him, Copernicus before him. And so then it started to become fashionable to be a man of science, and we started learning things again and started figuring out things again. And that's where Andy Dalton comes along, early 1800s. So he's about 150 years post Newton, and so he's definitely learned his physics, and so they're talking about matter and how it behaves and such. And then he just starts asking questions. Well, why does this material behave this way and this other material behave this way? And a lot of it was carried over from alchemy knowledge, which was the precursor to chemistry. It just had a lot of ritual, religious practices. I think it's because Dalton didn't really invoke alchemic rituals. He just extracted useful information. Okay, and so, some stuff is different than others. Well, is there anything that's ever pure stuff? And then, the blacksmith knows pure stuff, and that's forging and metallurgy hand in hand. And so, in the 1800s, we've got gunpowder, for God's sakes. So, and we definitely have steel swords and also steel barrel muskets. And so, maybe a little bit of knowledge from blacksmithing, maybe a little bit of knowledge from alchemy. We really started to figure out, and Dalton pushed the idea of maybe the Greeks were on something with this smallest indivisible part of matter, this atom thing. And so he said that stuff is made out of atoms, and the atoms can be different kinds of atoms called elements, and different elements have different atomic masses, and the elements form, I'm not sure if he coined the term molecules or not, but he definitely talked about atomic bonds, that is, atoms would link together. He didn't know they were sharing electrons. He just thought that they stuck together, like one of them had a little eye hook, and then the other one had a little fish hook, and they came close to each other, and the fish hook latched in to the eye hook, and then the atoms would stick together. And so the ball and stick models, like you see, this is the DNA double helix and that's the one from the set of The Big Bang Theory. If you've ever watched that show, it's sitting right by the entrance to the boys' apartment. But that's a ball and stick model. That's Dalton's model for the atom. So the atom was a spheroid, and different atoms had a different different number of linkages or bonds that they could form with other atoms. Carbon, he knew, could form 4 bonds. Oxygen typically formed only 2 bonds, and so on and so forth. Okay. Well, Mendeleev, working, I believe, in Russia, was also thinking about atoms, and he noticed that elements could be sorted by mass, but they could also be sorted by behaviors, such that you can arrange them in a chart or a table, and if the table repeated and looped back on itself, then you can line up the columns to have elements that have similar behaviors. And basically his chart was the periodic table of the elements. Okay. So we started chasing these elements, right? We just started, and I believe you heard about J.J. Thomson and his discovery of thallium, and that was around 1846. So remember, Dalton was here in the early 1800s, and so just 40, 50 years after Dalton, we're already to thallium on the periodic table. Okay. Now, we didn't go sequentially in order. Some of these elements, we skipped over several elements and filled it in sporadically. But there was a series of tests that physicists and chemists started developing in order to figure out the chemical properties and put it, and when they named an element, wanted to put it in the right place in Mendeleev's table. Okay, and so that's where we got the Crookes tube, and then Geissler invented a tube. Now Geissler's tube was kind of neat because he put in neon because he knew it was non-reactive, and he found that he mixed the neon with air and reduced the pressure, he could get the entire tube to light up. Well, what that was the neon atoms were getting excited and they were glowing and giving off light. Okay, the Geissler tube is the precursor to neon lights like you see down on Broadway and 2nd Avenue. And so, yeah, physicists did that. The Crookes tube, J.J. Thomson used a Crookes tube, just like Rankine used a Crookes tube to discover X-rays. J.J. Thomson was working with a Crookes tube, and he was more interested in the cathode rays that everyone knew about. The cathode rays were the useful part of the Crookes tube and the Geissler tube for performing these experiments on these elements and figuring out their spectral colors that they emit when they fluoresced, when bombarded with electrons. And again, that's electron excitation, same thing that's happening inside a neon light. And that was one of the tests for element identity, was this color test, this spectral test. Okay. Well, J.J. Thomson was really more investigating the cathode rays themselves, and he theorized that they weren't rays at all. They were actually particles. So here we go again with, is it a wave, is it a particle? No, J.J. says these are particles. And he says that they're not rare. Every atom of everything has these particles in it. Okay? And he named these particles electrons, and he said that they're negative, according to Franklin convention of electricity, these particles behave like they're negatively charged. Okay? And so he called that the electron, right? And so I think that was 1896. That was like literally 6 months after we discovered X-rays. J.J. Thomson renames cathode rays as particles that are our electrons. Okay. So he does this experiment, and I've got a video of the experiment that I'm going to play live. And I'm also going to show you the experiment. But he really doesn't get that much information about what else the atom is made of. And so he just tries to make up a model of the atom that's different than Dalton's, because Dalton has just got a solid sphere. But J.J. Thomson said, well, there's bits in that solid sphere that you can pick out and easily remove. Kind of like plum pudding. But we're not British, so we don't know what the hell plum pudding is. I think it's a Christmas dish. Never had it. Okay? But I have had raisin bread. Okay, so raisin bread, it's got raisins in it. But if you don't like the raisins, well, I would actually suggest you go find another loaf of bread that doesn't have raisins in it. But you can, if you're stubborn, you can pick them out, but then you'd have a piece of bread with a bunch of holes in it. So maybe go find another loaf of bread. But the raisins in regular raisin, not artificial raisin bread, where it's just raisin flavor goo injected into the bread like they do with the blueberry muffins. No, real raisins in the bread could be picked out. Okay. Well, Thomson, his model is really only addressing the electron behavior. He doesn't really have a good idea about the rest of it. So he just says, well, it's this positive matrix of goo, the bread loaf, that the negative charges are embedded in because opposites attract, so I satisfied that. And then maybe these negatively charged particles are really, really small, and that's why they're easily removed. It's because it's very easy to move smaller objects than it is larger objects. But he really didn't say anything about the bread much. He just said a positive goo. Didn't really say if that was a solid or if it was more of a vaporous cloud or what. So that bothered one of his colleagues. Might have been a student of his. I'm not up on my... I think Rutherford was a student, but not in 1907. I think Rutherford had moved on and had gotten a paying position as a professor. But I think Rutherford was at one time a student of J.J. Thomson. And so this is 1907. This is a little bit more than a decade later, like 10 years later. We're still trying to figure out what the heck the positive goo is. And so Rutherford, on the heels of radioactive particles, Marie Curie and Henri Becquerel and Pierre Curie, on the heels of the discovery of radioactive isotopes, Rutherford said, I could use one of those as a subatomic gun. If I could find a sample of a radioactive rock that I know is an alpha emitter, I could put it into a lead box with one hole in the front. Okay? And then the alpha particles would come out that one hole or collide with the inside of the box. Right? And then I could aim them at a very thin piece of stuff. Now, what stuff can we make the thinnest? And the answer was gold. Gold is extremely malleable, and you can make it thinner than a piece of paper. Okay? And so he got some gold foil. He said, well, if there's a positive goo, then we shouldn't see, now I think of it a different way. He said we shouldn't see any deflection at all. And so the alpha particle should pass right through the positive goo because apparently it's a diffuse cloud of positive goo. whereas the alpha particle is definitely a concentrated mass, like a bullet. And so if JJ is right about this positive goo, we should see it go right through with no deflection. See, in my original thoughts, how I first pictured it, this is just the way I learned it and what I thought they were saying with the plum pudding, was that the rest of the atom was solid positive goo, such that if the alpha particle intersected this positive goo, there'd be electrostatic repulsion and you would see all of the alpha particles ricochet. But Rutherford was thinking you would see no ricochet. You would see it would obey inertia. It would go through the positive goo and continue on a straight line path. And that is in fact what most of them did. But occasionally he would get either a small angle or a large angle deflection or a scattering of the alpha particles. Okay? And so that surprised him. That didn't make sense with either vision of the positive goo. That result doesn't make sense. With the positive goo being a vapor that doesn't really have a concentrated mass, it's kind of spread out all over the place like a fog, then you wouldn't see any deflection at all because there's nothing to ricochet or bounce off of. The charge isn't concentrated in one area. But if it's solid all the way through, you would see 100% ricochet. But that's not what we get. We only get sporadic partial ricochet, with most of them going straight through. So it must be that most of it is this miasma cloud, this nothingness, okay, that doesn't really have form, doesn't really have a concentration of anything that could create a ricochet. Most of it has to be that. But part of it has to be a compressed mass with positive charge in order to deflect the alpha particle. And so what he concluded was that atoms had a nucleus and the atom was mostly empty space. And if we're doing a live lecture, we will go to this and view the animation of the Rutherford experiment. All right. So that's great, right? Everything's solved. The electrons are removable from the atoms, and the nucleus is the concentration of mass at the center of the atoms. And the reason the electrons are around the outside of the atom is because they're orbiting the atom. Except for when you solve the acceleration equations for those electrons and try to plot their orbits, you realize that they have to keep losing kinetic energy, and they will something about the way classical mechanics approaches the electron as a particle. It spirals, it goes into a death spiral, kind of like a whirlpool, and eventually crashes into the nucleus. And so it didn't work. Rutherford's model had a mathematical flaw to it. The electrostatic attraction indicates that all electrons would death spiral into the nucleus and then eventually collide with the nucleus. And so Niels Bohr said, well, no, that's not possible because they can only exist in certain energy states. And so they can't lose energy because they can only exist at these, only reside at these certain energy states. And if they're not at that energy state, then they can't continuously lose energy. And that was the idea of shells, or orbital shells. Okay? And so Niels basically ripped off the planetary model of the solar system and said, like the planets are in stable orbits, the electrons are in stable orbits, but instead of physical pathways, those are energy states that they're in. Okay? And so he brought this idea to Rutherford. Rutherford liked the idea. He liked the idea that we were ripping off Newton because Newton was pretty smart and figured out the planetary model, and that mathematics was solid. And so Bohr and Rutherford agreed that it should be a planetary model, and there should be rules about how the electrons sit in different energy states. Okay? And so they started running tests, and lo and behold, the Bohr model was right about the energy states of electrons and such. But then some flaws were reported. And that's where we would go to the Schrodinger model to fix those flaws with the Bohr model. But the nice thing is those flaws don't affect X-ray science and what we have to understand. And so this is as complex as it's going to get, is the Bohr model with planetary orbits, but those are energy states. That's the only thing I want you to remember, is the Bohr model is not a picture of an atom. It's a model of the energy states of the electrons, not their physical positions. Okay? And so the K shell electrons are at a lower energy state than the L shell electrons. And I'll teach you those parts here coming up in just a second. Okay, so what we conclude, the state of the world right after Bohr publishes on the heels of Rutherford, this is the state of chemistry and the structure of the atom. Okay, and this is, I want to say, like early 1900s, so literally it took us about 100 years to go from Dalton to this. Okay, and then where we went from here is like an exponential curve. So we have a nucleus, and Rutherford said that the nucleus is a small, dense center where 99% of the mass of the atom is concentrated. That nucleus is made out of protons and neutrons, okay? And those are nuclear particles. That is, they are the particles that make up the nucleus, so they're nucleons, okay? Protons have a positive charge. Neutrons do not have an electric charge, okay? And then orbits and electrons. Electrons orbit the nucleus in a variety of planes, actually in a variety of cloud-shaped probability areas, if we're being specific. But these are not the physical orbits. They don't spin around in a circle like a merry-go-round. Okay? They do, however, reside in higher and lower energy states as they're whizzing around the nucleus. And so they can go to a higher energy state, they can drop to a lower energy state, and that process is called excitation or relaxation. That is baby steps right before ionization. Ionization is like super excitation, where you give the electron so much energy, it goes to an energy state where it doesn't feel tethered to the atom. All right, so yes, protons have positive charge, mass number of 1, okay? If you want to know the mass in kilograms, it's right there, but I'm not going to quiz you on it. Neutrons also have a mass number of 1. They are slightly heavier than a proton, but it's a 2/100ths of a kilogram. Not even that, 2/100ths of 10 to the 27th kilograms. So, yeah, a very small quantity of mass. And the difference is the mass of the electron. Okay, so if you add the mass of the electron to the proton, you get the mass of the neutron. That is not an accident. A neutron is now thought to be a proton and an electron that have fused into a singular particle. Okay. So the neutron is neutral. It weighs the same as a proton. The electron has such a small mass that we really don't count it in the overall mass of the atom. But it possesses a negative charge equal in magnitude, opposite in sign to the proton. So electrical stability or neutrality. Okay. So matter doesn't like elevated energy states. It likes to descend to what we call the ground state, or the lowest energy state possible. Okay. And so it will give off energy to do that. That's going to manifest by, first of all, balancing the number of charges within an atom. So if you encounter an atom, most of the atoms you encounter are going to have a balance of charges. Okay? You have to put energy in to get rid of some of the electrons to make the atom into an ion. Okay? And that is the number one way to make an ion, is to start removing electrons. And the reason is the energy difference. It takes roughly, on average, 3 electron volts to yank an electron off of an atom and free it. By contrast, removing a proton from the nucleus requires 931.5 mega electron volts. That's a whole bunch of energy. That's more energy than we use in radiation therapy. Forget about X-ray. Okay. Atomic number. The only time you encounter energies that big is when you're detonating a nuke. Okay, so it's very, very difficult to have enough energy present to pull a proton off of a nucleus and make an ion that way. It's far easier to pull an electron off of the atom and make the atom positively charged. Okay? Or to put an extra electron onto an atom and make it negatively charged. Okay? The atomic number. The atomic number is unique for each element, and it's literally just the number of protons in the nucleus. And so that's why oxygen is oxygen. Oxygen is really oxygen because it has a Z number of 8. Okay, so if you encounter an atom that's got 8 protons, that's oxygen. Now, is it an atom of oxygen? I don't know. Does it have 8 electrons? If it's only got 6, then it's an oxygen ion. You see? Okay. So that's the importance of atomic number. Really is elemental identity. It really, it's why we call oxygen oxygen. It's why we call hydrogen hydrogen. It's why these things have names based on the atomic. What does hydrogen mean? It means you're dealing with an atom that only has 1 proton in the nucleus. Okay. Now, the valence shell often determines chemical behavior. Okay? But the valence shell is dependent upon the number of protons in the nucleus plus the available energy states of the shells that you're populating with electrons. Okay? Atomic mass is the total mass of the atom, but it's estimated by just counting the number of protons and neutrons. Okay? And so therefore, the number of neutrons can be deducted by subtraction of these two numbers. You take atomic mass, which is always the bigger number, and subtract away Z, the atomic number, the number of protons, and the difference is the number of neutrons. Okay? So atomic mass, that is where we get isotopes from, because the number of neutrons can vary significantly. You can have carbon-12, which is the most common form, but you can also have 2 extra neutrons, and now you have carbon-14, and it's radioactive. Okay, and so you will get different chemical behavior also, because carbon-12 is not radioactive. You will also get different behavior from isotopes of that element. Okay, other atomic variations. Changing the number of neutrons or electrons does not change the element. Only changing the number of protons does. And so isotopes are when we change the number of neutrons. Ions is when we change the number of electrons. Okay? But remember, every ion is unstable and wants to return to a ground state with a balance of charges. And so ions, when they're created, they are highly reactive. They want to rebalance their electrons and protons. Okay? And so we get, with ions, we get chemical potential energy because it's more likely to be reactive to try to seek out an additional electron or to try to donate an additional electron in terms of a negative ion. Okay. And so orbital electrons are populated into shells, but there's a maximum capacity to the shells. So the principal quantum number plugged into the formula 2n squared determines the maximum capacity of any shell. However, there is a follow-up rule dealing with the outer shell, and so that one supersedes this rule. So max capacity of the first shell, which we have named the K shell, is 2n squared, where n equals 1. 1 squared is 1 times 2 is 2. So I can put 2 electrons in the K shell and then it's full. I can likewise put 8 electrons in the L shell and that one's full. And then 18 electrons kinda in the M shell. And that's where we first encounter the second rule. The second rule is the octet rule. Atoms don't like to have more than 8 electrons in their outer shell. And so for this reason, larger atoms begin filling in the next outer shell before the maximum is reached. So at 8, with the maximum being 18 for the M shell, you will fill the M shell with the first 8 electrons, and then you'll put the next 2 electrons in the N shell, N for Nancy. Then once you have 2 electrons in the N shell, then you can go back and fill in the rest of the electrons in the M shell. M for moon. Okay. Sorry, I speak very nasally and it's hard to tell the difference between those 2 word sounds or 2 letter sounds. M, N. I'm trying. Okay. Atoms with 8 electrons in outer shell are typically chemically stable and inert. All right, and this is over on the far right-hand column of the periodic table. This group, I think it's group 8 or family 8, depending upon how the columns are labeled. Those are known collectively as the noble gases. Nobility doesn't mingle with the rabble, and so these do not mingle and circulate with the other elements: helium, neon, argon, krypton, xenon, and radon. Those are all noble gases. Electron binding energy. Binding energy is a manifestation of the attractive force of the nucleus to the electron. Okay? And so it's related how close the electron in the Bohr model, how close it is to the nucleus. Remember, this is not a physical model, so the electron is not really closer to the nucleus. It's in a lower energy state to the nucleus. And so lower energy state means it's got a higher binding energy. It's got increased attraction to the nucleus. And so the binding energy increases generally when you're in the lower shells. When you get to the outer shells, you get lower binding energies in the same atom. But as you increase the number of protons in the nucleus, you increase that attractive force between the nucleus and the electron, and so the binding energy will increase. Okay. So electron binding energy primarily determined by proximity to the nucleus, that is the energy state, and the total number of protons in the nucleus. You can think of it as kind of a negative potential energy, and the reason I say that is because that's how Bohr described it. Bohr described the binding energy as a negative potential to leave the atom, and so that energy had to be supplied to the electron before the potential to leave would manifest. Otherwise, it's basically tethered to the atom as if it were chained to a post. Okay? And so this binding energy, expressed in electron volts, we can see that in this equation. And those of you who have seen my electromagnetic wave lecture have already seen this equation. This is the photoelectric effect. And so Einstein utilized Bohr's concept of a binding energy in his explanation of the photoelectric effect. And so this equation was proved experimentally with a simple reaction, and so it gave confirmation to the Planck equation, but also confirmation to Bohr's model of and Bohr's idea of binding energies. All right. And so periodic table of the elements. This is it's supposed to be a handy chart. I know. I don't like it either. It's got way too much information. It seems crowded with information. They could do a little bit better I think they can do a little bit better in explaining it, because I really didn't understand it until I got to college chemistry. Okay? And so I'm going to try to explain to you the way that I understand it now. Natural elements display periodicity. That is, you can start with hydrogen, and then you can add protons, and that's helium, and then add another proton, right? And now you are at lithium. But the lithium behaves like the hydrogen does in certain circumstances. Okay? And then you add another one, and then you add another one, and then before too long, you're back at something that behaves like helium. And there's a progression, and it follows with adding an electron. So the top row represents populating the K shell with electrons. And then the next row down represents populating the L shell. And so there's 8 individual elements on the L shell, and when you fill the L shell, then you have, I think that's neon, that's the noble gas. Okay. And so families and groups. So the vertical groups, that's what I was talking about families of elements. They display similar chemical behaviors. They like binding to the same, to other families. Similarly, like typically you get group 7 likes to bond to group 1, and that's because group 1 has a lone valence electron, and group 7 has seven valence electrons. And so you see a lot of 1-7 pairs. Those are a lot of your salts are 1-7 pairs. Group 1 from group 1, 1 from group 7. And those are typically ionic salts. Okay. Horizontal periods track the pattern of placing electrons in the Bohr model shells. And then we have the atomic element symbol, which is important for chemical formula shorthand, because you don't want to write out nitrogen every time. Nitrogen plus oxygen equals nitrogen dioxide. Well, that takes a lot of chalkboard space. So why don't we just say capital N is nitrogen and capital O is oxygen. And then a subscript 2 means there's 2 oxygens. Okay? And so if we have N2, which is nitrogen gas, plus O2, how do we get nitrogen? Well, we need 2 oxygen gas. So N2 plus 2 O2 yields 2N2O, and then we have a balanced equation. Yes, the number of atoms on one side balances the other. Okay. The atomic weight is sometimes given, so 14.01 is the average atomic weight versus the atomic mass is more you're dealing with a specific isotope of nitrogen versus the atomic weight is the average atomic mass across all isotopes. And typically the whole number that it's closest to is the most common isotope. So for nitrogen, nitrogen 14 is the most common version of nitrogen. Okay? That's just how averages work, right? And then usually the Z number is the smaller number and it's separated from the atomic weight. They do like to put the Z number in the upper right hand corner in most cases. I have seen it in the upper left and with the atomic mass in the upper right, but all you have to remember is the Z number is the smaller of the two numbers and you'll never miss it up. Okay. So horizontal period, same number of electron shells on the rows. The vertical families or groups have the same number of valence shells, and the chemical behavior is often, a lot of the chemical behaviors are determined by the valence band. That is the population of electrons in the, does it have 4 electrons or 6? Because they all want 8, okay? Chemical combining characteristic determines how the atom will bond with other atoms. So a +1 means the atom is likely to donate an electron. A -1 would mean the atom is likely to borrow 1 electron. Oxygen usually has a -2 as far as combining state goes. It wants to borrow 2 electrons really, really badly. Right, so here's a periodic table, and they've got everything in red, and this is a copy of the image in your book. So a lot of this is too small to read. You can make out the Z numbers; those are the black numbers above the shorthand name for the element, and I've highlighted the ones in green that show up pretty frequently in X-ray science. So we'll start with hydrogen. And then moving over to carbon, nitrogen, and oxygen. Well, those are the organics, ladies and gentlemen. Most biologic material is made out of a few trace other elements, but primarily made out of those. I wonder why boron was skipped. That is strange. Carbon, nitrogen, oxygen, and hydrogen. Okay, if you have that stuff, you could make, well, a little bit of calcium and such, but you can make a bacteria. If you wanted to make a frog, you would need some calcium and some phosphorus and other trace minerals. But yeah, hydrocarbons, if you want to make DNA, you can use just hydrogen, carbon, nitrogen, and oxygen. So those are called organic elements. Technically, anything that's not a metal is organic if you're talking to a chemist. But hydrogen, when it's inside a star, behaves metallically. So it's not it's an organic, but it's also a metal. So then going down, the next relevant molecule to X-ray science is calcium because it participates in the photoelectric effect in the bones. Iodine, barium, tungsten we use in the X-ray tube itself, and then lead we use the biggest and baddest, highest atomic number. We use that to shield ourselves from X-rays because lead is one of the It's a stable, common element in the Earth's crust. It is a neurotoxin, so don't get the dust on your hands. Wash your hands after you get the dust on your hands, because you will grab your cheeseburger with lead dust on your hands. Lead's a neurotoxin. Okay? But lead is really, really good at absorbing X-rays, so that's why we use it for our shielding. But we take shavings of lead and we embed it in liquid rubber, and then let the liquid rubber cool in flat sheets, and then we cut it up into sections and sew it inside a canvas. And now the rubber stops with lead, little flecks of lead embedded in it, stops the radiation it absorbs. It's got enough lead that it absorbs. So, all right. So that's it. That's the atomic theory in a nutshell. That's, yes, there is the, and the book might even mention the Schrodinger model. I think it's a waste of our time. Yes, the Bohr model is not accurate. The Schrodinger model is more accurate with our modern understanding of both the electron and the atom. But for the sake of explaining upcoming phenomena like bremsstrahlung, characteristic cascade and emission, photoelectric effect, Compton scatter, those type of things, we're going to be using the Bohr model, so we can stop our understanding of the Bohr model. Keep it. If you don't need the more complex model, then why use it? Why not use the one that is easier to understand and makes sense of the things you want to explain coming up? And that's what the Bohr model does. And so, yeah, I'm happy with the Bohr model. So, yes, I understand it's not realistic. It's got so many flaws to it. I don't care. That's what we're using. All right. See you guys next time.